In the previous video, we started our discussion of the transparent conductive oxide layers. We discussed the need of many thin film technologies for a transparent layer with high lateral conductivity, and we saw how transparent conductive oxides are the best available option. Now we take a look at the performance of an aluminium-doped zinc oxide layer. As discussed in the previous video, the red, yellow and blue areas represent the absorption, reflection and transmission of the TCO layer respectively. We also discussed how the increased free carrier absorption can be explained with the Drude model of metals. This model describes how the free charge carriers in a semiconductor or metal absorbs the light, usually in the infrared spectral range. In the Drude model, the frequency-dependent electric permittivity is given by this equation. The first part shows that the complex electric permittivity is equal to the complex refractive index squared. The second part describes the complex permittivity of the TCO as a function of the frequency omega, the plasma frequency omega p, and the relaxation time tau. We can rewrite this equation so that the complex permittivity now contains a real part denoted by epsilon 1 for convenience sake, and an imaginary part. We can gather that the imaginary part of the dielectric function decreases with increasing frequency. The imaginary part of the dielectric function is directly related to the imaginary part of the complex refractive index, which is the extinction coefficient. As we may recall, the extinction coefficient is directly related to the absorption coefficient according to this relation. Therefore, as the imaginary part will increase with decreasing frequency, the absorption by the TCO increases with increasing wavelength. Furthermore, as we can see, when the photon wavelength is greater than the plasma wavelength, the TCO starts to become highly reflective. For applications in solar cells, the TCO should be highly transparent in the active region of the absorber, which for example is this region for crystalline silicon. Therefore, the plasma wavelength should at least be longer than the wavelength of the absorber. The plasma frequency is proportional to the free carrier density Nf, the effective electron mass Me, and two physical constants being the elementary charge Q and the electric permittivity of free space epsilon naught. The free carrier density is an important parameter for the conductivity of the TCO. Generally speaking, the higher the free charge carrier density, the greater the conductivity of the material. We can gather from this equation that a longer plasma wavelength corresponds to a lower free carrier density. Finding an optimum between high transparency and high carrier density is a challenging process in TCO design. Let's look in more detail at the trade-off between transparency and conductivity. In this graph, we can see a typical absorption spectrum of aluminium-doped zinc oxide. This TCO has been processed with the sputtering technique in this example. In the visible part of the spectrum, this aluminium-doped zinc oxide is highly transparent, but the absorption rapidly increases for wavelengths larger than 800 nanometers. This is in the spectral range that many PV semiconductor materials have a photo response just above their band gap. This means that aluminium-doped zinc oxide can significantly contribute to the parasitic absorption losses when it's integrated into the front window layer or even as a part of the back reflector. Here you see the absorption spectrum of intrinsic zinc oxide. Intrinsic means that no intentional dopant like aluminium has been added to the zinc oxide. The free carrier concentration of intrinsic zinc oxide is much lower in reference to the aluminium-doped zinc oxide. As a result, the Drude absorption in the red and infrared part is much lower than for aluminium-doped zinc oxide. However, the resistivity of the intrinsic zinc oxide is much larger in reference to aluminium-doped zinc oxide. This means that in a PV device, only a relatively thin layer of intrinsic zinc oxide can be implemented to prevent a significant increase in the series resistance. The resistivity and transmission of TCOs depends on the carrier density. The interplay of these properties can depend on the doping types, size of the crystalline grains, defects in the materials. Therefore, the thin film preparation procedures such as deposition methods, annealing techniques, and dopant type can play a role. For example, here you can see the absorption spectrum of boron-doped zinc oxide process using low-pressure chemical vapor deposition. The main difference are, first, the dopant aluminium is replaced by boron, and secondly, the low-pressure chemical vapor deposition technique results in denser zinc oxide films in reference to using the sputtering method. This boron-doped zinc oxide shows higher transmission in the red and infrared, while a low resistivity is still preserved in comparison to aluminium-doped zinc oxide. Hydrogenated indium oxide is an example of a TCO material developed at AIST by Koda-san that has a low absorption spectrum in the red and infrared similar to intrinsic zinc oxide. However, the advantage of this material in reference to intrinsic zinc oxide that it still has a low resistivity. Of all the TCO materials currently available, the trade-off between transparency and conductivity is best for indium tin oxide, or ITO. ITO is used for a variety of applications, among which are your mobile phone and flat-screen TVs. Indium is, however, a rare earth element with a very low abundance of 0.05 parts per million in the Earth's crust, which is about similar to elements like silver and mercury. This makes ITO less preferable for cheap, large-scale PV applications. Other TCO materials are therefore thoroughly investigated and used in industry. The most promising among them is the earlier discussed aluminium-doped zinc oxide, or AZO. The materials of AZO are non-toxic and inexpensive due to an abundance of about 8% for aluminium and 65 particles per million for zinc. Other alternatives are boron-doped zinc oxide and fluorine-doped tin oxide. The abundance of boron is about 11 particles per million, fluorine is about 525 particles per million, and tin about 2.3 particles per million. However, another important aspect of the implementation of TCOs that should be considered is its resistivity to water. Zinc oxide is more susceptible to humidity-induced oxidation compared to tin oxides. In summary, we discussed the substrate and substrate deposition sequences and saw that both require a transparent front electrode. We looked into several materials available for such an electrode and found that transparent conductive oxide are the best available option. We discussed the transmissive absorption and reflective properties of a TCO layer and the important trade-off between the conductive and optical properties. Finally, we considered the best performing TCO, known as indium tin oxide, and also some less expensive alternatives. In the next video, we will discuss another important concept for thin film technology, namely the multi-junction solar cell.